Okay, so we are finding the flux, all right? And I ask you to use the divergence theorem, which means in order to find this flux, you can just go ahead and use this triple integral, which is the easy way. But before I go over your solution, let me tell you why you do not want to use the left-hand side. This is the direct way to find the flux, right? The definition of the flux, it is the double integral of f dot n ds. So you take the dot product with the normal because you want to find the normal component of the vector field f at every single point x, y, z on the surface S, and you integrate it. And of course, the way you calculate this, as we have seen before with surface integrals, is to take the dot product of f with RU cross RV, which is the normal component, right? And so you would have to parameterize the surface S. The problem is this is a rectangular box. You have 6 sides. Each side is a rectangle, right? And so you would have to do this parameterization 6 times and find the normal component and add them up to find the flux. You probably do not want to do that because it would take you a long time to parameterize and analyze the 6 sides. So I will just show you one and see what happens. Let's pick one side of the 6 sides and how you find the flux over on that one side. So for instance, let's pick this side here. Okay, this is the side where y is equal to 1. Okay, this is the side that is facing this way. And so how do you parameterize this? Okay, so I can parameterize it in 2 different ways or maybe many ways. But on this side, which is the side where y is equal to 1, I'm going to parameterize this 2 by 3 rectangle this way. R of u cross uv is v1u. Now, you probably are asking, why didn't I put u1v? Well, it doesn't matter, right? Okay, the reason I want to do this is because I want my cross product to come out in the right orientation. So let me explain what I mean by this. Right, by switching what is traditionally U1V, to V1U, my RU will be 0, 0, 1. My RV is of course 1, 0, 0. And when you do the cross product of these, okay, you get what? 0, and then the middle one will be it's 0 minus 1, so it's -1, but then you have the minus, so this will be 1, and then the last one is 0, right? So this is not a surprising thing. You got this vector 0, 1, 0, which is the one that comes out this way, right? So at every single point, the normal vector comes out that way, and that is good because we are trying to find the flux of the thing, the object coming from the inside out, right? So how much is coming out from inside of this box to the outside world? That is what we are looking for. So, and to answer this question, why didn't I write U1V? Okay, actually I did that in my previous recording, which I will now destroy, because when you do it this way, the orientation reverses, and then I would have to switch the sign, and there's sort of something messy in order to calculate the flux from inside the box to the outside world. And so sometimes you have to make these adjustments like this. Okay, but don't worry too much about this. What we will now calculate is the flux on this side where y is equal to 1. Okay, so we have a normal, right? And so the normal has the right orientation from the out, from in to the out. And f is xy squared z squared. On this parameterization, this is my parameterization. So this will be v1, sorry, so it's 1 square, which is 1. And then z cubed is u cubed, right? This is my f. So f dot ru cross rv is simply 1. You get that? That's not bad, right? So then the double let's say this side is, let's call this S1. Okay, so that side is S1. And so the flux over the, or I should say flux across S1 is what we just calculated. You have to integrate this. Okay, but I mean, this is really not all that bad, right? Because we just found out this is, let's say, this is 1. And we are going from, U goes from 1 to 3. Oh, is that right? No, I think u goes from 1 to 2, right? And then v is the x coordinate, so this goes from 1 to 3. That doesn't matter. So this is 0, 3, 0, 2, and then 1, and then this is d, u, d, v. Okay, but regardless, I mean, this will just be 6. Okay, so what this is saying is that whatever is described by this vector field of f, okay, 6 units is coming out of this side, which is the side where y is equal to 1. Okay, now you do this. Now do this with the other 5 sides, and then you add the flux, and you can get the flux of the f across that surface S. Okay, or you can use the right-hand side of the divergence theorem. All right, so it says the flux of f across S, the entire surface, is equal to the triple integral over the entire solid, the rectangular angular box of the divergence of f dv, right? And you will see it's much easier. Well, the calculation could be messy, but what is the divergence of f? You know f is this, right? So the divergence of f is not a vector, first of all. It is going to be the partial. Yeah, let me go ahead and write this. It's px plus qy plus rz. That's the definition. So what is the partial of x with respect to x? That's 1. What's the partial of y squared with respect to y? That's 2y. And the partial of z cubed with respect to z is 3z squared. So that's what we have to integrate, all right? Remember, I can use any order. I'm going to use the typical order of dz, dy, dx. So x goes from 0 to 3, y goes from 0 to 1, z goes from 0 to 2, and all I have to worry about now is to integrate this dz, dy, dx in this order, okay? And the rest is pretty simple. You know how to do this. Z plus 2yz plus z cubed. I am integrating this with respect to z. And then you go from 0 to 2. I would, if I were you, I would try to follow along and make sure you can do each step. So when you plug in 2, you get 2 plus 4y plus 8. And then dy dx, and this happens to be 4y plus 10 dy dx, and I'm missing something here. It's supposed to be 0 to 1. Okay, and so this will be 2y squared plus 10y going from 0 to 1. And this will be, if you plug in 1, of course, you get 12 and dx, and that is 36. So the answer is 36, and 6 was coming from that side where y is equal to 1, and you can do that with all the other 5 sides, and then if you add them up, you will get 36 as your total flux, okay? And that's how you can use the divergence theorem once you understand the the role it plays in the big context of vector calculus and all of these fundamental theorems. Okay, let me give you another example, and then we'll work on that. This time, I will give you, maybe I'll do this in both both sides of this. All right, so here's the second one. All right, let me give you E is the unit sphere. Actually, I shouldn't say sphere, because when you say sphere, that's so bad. All right, let me go ahead and do this a little better way. When you talk about a sphere, technically what you're saying is only the outside, the two-dimensional, just the surface of that ball. So I will call this the solid ball, and you can see equator. See, without this equator, it just looks like a circle. So I like to make it look, real, three-dimensional ball by having this thing in here. All right. So I hope you have you caught what I just said. When I say the ball, I mean solid ball. That is a sphere and everything inside. Okay. So the radius, because it's a unit sphere, the radius is 1, and the center, of course, is the origin, 0, 0, 0. And if you're only talking about this outside surface, that would be the unit sphere. But if you include all of the points inside, that's called a unit ball, okay? And so that is my E. And of course, if you are to, graph in your normal vectors, they all look like this. They're perpendicular, to the surface, the unit sphere, and so on. And then the question now is, of course, how much of the stuff is coming out? Let me give you F. F is very simple, X, Y, Z. Oh, by the way, X, Y, Z means that at point like 1, 0, 0, the vector is 1, 0, 0, right? So it is basically in the same direction, or it's a direction that is going away from the origin. This is the one that goes away from the origin in all the directions, okay? Just like something exploding at the origin or something. It's just going in away from the origin, completely in opposite direction from the origin. And of course, the vector gets longer as you go farther and farther away, right? So this is the kind of vector field we are talking about. Find the flux of F over the surface S. And surface S is, of course, the unit sphere. Okay, so E is a solid unit ball and S is its boundary, which is a unit sphere. Now the answer is going to be definitely positive because as you can see with this vector field, everything's going away from the origin to the outside, right? So again, if an energy is exploding from the origin, according to this vector field, then the flux will be definitely positive. Let's go ahead and calculate this in both ways. So maybe the question would say something like this: verify the divergence theorem, which means that find the left-hand side and find the right-hand side and show that they are equal to each other. Okay, so what we have to do is to find the flux, which is the double integral or O of F over that surface. So that's going to be written this way. And then the right-hand side will be the solid E, triple integral of solid over solid E of the divergence of F, right? One will be much easier than the other. But let's go ahead and do the left-hand side first, and then do the right-hand side next. All right, the first, left-hand side, I have to parameterize the surface, right? How do you parameterize S? The sphere, okay? Well, that's going to be, we are going to use a standard parameterization of the sphere, which is not so easy, if you remember. That is sine U cosine V, sine U sine V. This may remind you of the spherical coordinate system because that's pretty much what it is, okay? Where U represents the, like our variable phi, and V represents our variable theta, which goes from 0 to 2 pi. Okay, so if you go back a few sections, you will see that this is indeed the A, or so the most common parameterization of the sphere of radius 1. Okay, because there's no coefficient in front of it. Okay, so you can do RU and RV, and we can do the cross product. This is sort of automatically done. If you have been studying this, you know that you have to calculate these things in order to find the double integral, which is on the left-hand side of the divergence theorem. All right, so what's RU? This is cosine U, cosine V, cosine U, sine V, and then negative sine U. RV is negative sine U, cosine, no, it's not cosine, negative sine U sine v, and then sine u cosine v. Remember, we are just taking the derivative with respect to v, so the last one will be 0, okay? So then you calculate, and this is a big product here, but it's going to be 0 minus negative of, so this will be positive sine square u cosine v. I strongly encourage you to do this on your own and follow along. And then the next one will be positive sine square u sine v minus 0. And then the last one will be the long one. You have sine u, and then cosine u, and cosine square v minus negative, so it's going to make it positive, sine u cosine u sine square v, okay? So be very careful distinguishing your u's and v's and so on. And you can probably tell this is sine square u cosine v, sine square u sine v. And what do you have for the last one? You see sine u cosine u, and then the rest of that, if you factor out sine u cosine u, which you see in both of these, the rest is cosine square plus sine square, otherwise known as 1, right? So this is your parameterization, or RU cross RV. All right, so F, remember what F is? It's X, Y, Z. In this case, X, Y, Z is, well, let's see, X is, let me go ahead and write this. This is the X, this is Y, this is Z. And so X, Y, Z is simply sine U cosine V, sine U, sine V, cosine U. All right, U dot RU cross RV. You take the dot product, okay? So this will be sine cubed U cosine square V plus sine square U sine square V plus sine U cosine square U, right? And so that is what you would have to integrate. So the flux on the right-hand side will be, remember, let's see, V goes from 0 to 2 pi, U goes from 0 to pi of this whole thing. Now, is there anything I can do to simplify this? One thing I can do is to take out sine U, I guess, right? And then you have sine cosine. Yeah, maybe I should have written that. Let me go ahead and do that. Okay, so at this point, you notice that we have sine cubed U in the first two terms, right? And so let's factor out those from the first two terms, and then the remaining part is cosine square V plus sine square V. It's always a good sign when you see sine square plus cosine square. And then the last one is sine U cosine square U, right? But the point is, I mean, this is of course 1. So this is sine cubed U plus sine U cosine square U. You can even do better than that. You can factor out sine of U from both, and then you have sine square U plus cosine square U. What do you know? The dot product of F and the cross product of RU cross RV turns out to be sine of U, and therefore the flux on the right-hand side will be the double integral of sine of U, right? I should not be doing this. Let's go ahead. At this point, since we are using U and V, I really should be doing the double integral with the bounds, right? In this case, let's see, 0 to 2 pi, the V goes on the outside and U goes on the inside, sine U du dV. Okay, so that was not too bad, because this time we didn't have 6 different sides to parameterize and integrate, right? This is just one surface with one parameterization, which is the sphere, which is complicated, but you know, things work out very nicely using trigonometry. So this is 2 pi, 0 to 2 pi, and then what's the antiderivative of sine of U? That's negative cosine of U going from 0 to pi. And so this is what you get. Now, what's the negative of cosine of u? That's negative 1 minus negative cosine of 1. So this is what you get. It's always tricky when you have so many negative signs, but this basically says 1 plus 1. So that's 2 times 2 pi. The answer is 4 pi. So going back to that, remember everything's coming out like this, and of the unit sphere, and it turns out the total flux of that energy or fluid from inside the spherical bubble to the outside world turns out to be 4 pi. Okay, check mark. Right-hand side. The right-hand side says the flux is the triple integral over E of the divergence of F dV. Okay, so F was XYZ. What's the divergence? It's 1 plus 1 plus 1. Right? Because the partial of x with respect to x is 1, the partial of y with respect to y is 1, and the partial of z with respect to z is equal to 1. So this turns out to be just 3 dV. And of course, this is 3 times the volume of E. And what is the volume of E? It's 4/3 pi r cubed, right? So this is, of course, 4 pi. We are done. And so, sometimes one side is much easier. And this is the power and effectiveness of the divergence theorem. Okay, so I think you are now able to do your homework for the last section, section 6.8, except the last half of the homework is basically teaching you how to use or which theorem to use for which problems. Okay, so in order to help you out on that, I have another video which you should watch before you start doing your homework. Okay, and that is a summary of all of these theorems in chapter 6. Okay, so why don't you watch that the summary video for all of these theorems in chapter 6, and you have a handout on that. And so take out and print out the handout before you do that, before you watch that video. And as you watch the video, you can fill in the form. And by the end of that, I hope you can learn, or you will know, which theorem to use for which problem or which type of problems. All right, so hopefully you'll do that, and then you should be all set to do your homework for the last section of Calculus 3.